Good afternoon, and thank you for joining us online today. I'm Peter Kurczynski, Program Director at the National Science Foundation. Scientific discovery has immense benefit for society and inspires a sense of wonder about the universe. And few things capture the imaginations of those who are interested in the universe like black holes. Today we're going to take a look back at the historic discovery announced 1 year ago by the Event Horizon Telescope collaboration, look at what's happening now, and look ahead toward the future of this collaboration. A black hole is unlike a star or any other object. Its defining feature is its gravity. We all know about gravity because we know about the dangers of falling, but a black hole is a terrifying place where the falling never ends. Even fleet-footed light rays, the fastest things in the universe, are deflected, warped, and even swallowed whole if they stray too close. Words and superlatives fall short in describing black holes. Some astronomers simply call them monsters. They are believed to lurk in the hearts of galaxies where they have swallowed masses equivalent to millions or even billions of suns. Paradoxically, the environments around these monsters can spew jets of radiation for thousands of light years and alter the fates of galaxies. How they do this is largely unknown. Until 1 year ago, the black hole was still just an idea. No one had ever actually seen one. Then on April 10th, 2019, in a synchronized worldwide public release, the Event Horizon Telescope collaboration revealed its first image of a black hole at the center of the galaxy M87. This image was seen around the world. It was featured in virtually every major news outlet. Even official Washington seemed briefly unified with a sense of awe and wonder at this new vista revealed to us by science. In terms of impact with the public, this one event moved the needle for the National Science Foundation, by one measure tripling its footprint on the internet and giving our web platforms a whole new audience and many new fans. We are privileged today to celebrate the 1-year anniversary of this announcement and explore the Event Horizon Telescope's ongoing work with two members of the collaboration. Its founding director, Sheperd Doeleman, Senior Research Fellow at the Center for Astrophysics, Harvard and Smithsonian, and Michael Johnson, also a research scientist at the Center for Astrophysics and a member of the Event Horizon Telescope Science Council. Shep and Michael, welcome to this event and thank you for joining us. Shep, would you like to share a few words?
Yeah, thanks very much, Peter. It was a wonderful introduction. This is a very special time for us, for the Event Horizon Telescope collaboration. It's been a year. We've had a chance to digest this discovery and to share it with the scientific community and more broadly with the public. And that's been a major part of our mission. We really do see ourselves as explorers going to the edges of the universe and coming back to report on what we've seen. And that's our sacred compact, if you will, with everyone that funds us and supports us. Scientifically, it's been quite amazing. We, in one image, were able to verify Einstein's predictions writ large on the sky. We saw this ring of light where you get photons being bent in the immense gravity of this black hole. And more than that, it was a confinement of 6.5 billion times the mass of our sun, some compact object within this photon orbit. And that was really revelatory. It was the first time we'd seen Einstein's theories in that astrophysical context on that scale. And it, more than that, even, it opened up a new path for discovery. So just as you take the first look through a microscope and you see your first microbe, and that leads to a whole field of study. Now we feel that looking at this first black hole is going to open up a whole new field of precision measurement of the event horizon, allowing us to make ever better and more precise tests of Einstein's theories, and really to understand how black holes digest all the gas that falls into them, and as Peter said, erupt with jets and outbursts and power a lot of the universe that we see. And then personally, I have to say that it was quite an event. To be able to share this with the public was really something. We've been working on this, some of us, for 20 years. We started with a small team, and with seed funding from the National Science Foundation, who really believed in us, and from others, we were able to build it to a 200-member strong collaboration. That's really what this is about. We reached out to experts across the globe to make a global team. And that's what you need to build a global telescope. And we did this only by sharing resources across borders, across countries, across expertise and fields. And especially in these troubling times, it's such an encouraging feeling to have been able to do that, to get everybody together to focus on what we thought was an impossible problem. And so beyond that, the question I get most often is what's next? It's very natural. It's a human question, right? What we're doing now is we're working on the data still to give us even better looks at the event horizon of the two objects that we look at, Sagittarius A star and M87. And beyond that, we're looking to increase the capability of the array. So scientists are always hungry for the next instrument, the next observation. And so we're looking at something called the next generation event horizon telescope, which is going to give us even sharper views and let us make the first movies of black holes. And it's changing the discussion. It's changing how we think about these objects. And one of those ways is that we can now think about getting such precise angular resolution that we could zoom in on this photon ring itself that we've seen and allow even ultra precise tests of Einstein's theories and even extraction of spin. And that kind of leads to what Michael Johnson's working on now. He's kind of pioneering and leading a new effort that's I think is very, very exciting. So I'd like to hand it over to Michael now.
Great. Well, thank you, Shep. And let me start by thanking the NSF for coordinating this event and to all of you for being here during these extraordinary times. It's really an honor to represent the hundreds of scientists around the world who have made the EHT collaboration a success. This collaboration simply would not be possible without dedication of telescope operators, engineers, data scientists, calibration experts, and astrophysical theorists who have come together with a unified vision to study black holes by directly watching them in action. Black holes are one of the most profound success stories in theoretical physics. They began as an idea, an inevitable consequence of a new theory of gravity that was born from a combination of new experiments and human ingenuity. Over decades, they moved from being a mere theoretical curiosity to taking their place as a cornerstone in our understanding of the universe. And we now think that black holes are commonplace, as Peter said, sitting at the center of every galaxy and driving the most energetic events in the universe. But even as our understanding of their role in galaxies has become increasingly nuanced and complex, black holes have remained profoundly simple. Supermassive black holes are elemental objects described only by their size and rotation. And this simplicity is a wonderful opportunity for experimental science to put our most successful physical theories to the test using objects with precise and immutable predictions. Simply put, the predictions for black holes leave no wiggle room for creative reinterpretation. So publishing the first black hole images a year ago was a turning point for our collaboration. After years of focused work, we were finally ready to share our first results with the world. And this highlighted another rare gift of the project. And that's that a 10-year-old can be excited about black hole images for many of the same reasons as EHT scientists like Shep and me. People across the world were able to see beyond the dizzying technical complexity required to create the first images and to share in the joy and wonder of the discovery. So a year ago was an extraordinary moment of revelation, and the past year has turned that moment into a broad change in how we think about black holes and how we can study them as a community. So we're working hard to extend our analysis of data we've already captured, to expand the EHT array and to create sharper black hole images. And as Shep said, to even allow movies that would reveal the daily lives of these cosmic wonders. So we're really excited to be here to share more about these ongoing efforts. And with that, I'll pass things back to Peter.
All right, thank you. So now if you're a member of the meeting as a participant, you can start queuing up to ask some questions. And as that's happening, I'll go back to Shep and ask Shep if you could please just walk us through this image that's now been seen by so many people around the world and just give us a broad description of what exactly we're looking at.
Do we have an image? I think I probably have an image I can share. Can I share my screen?
Sure.
Yeah, I like to, can everyone see that?
Yeah.
Yeah, I like to share this image because it simultaneously shows the image, but also in the context of an XKCD cartoon, which is one of the highest honors, of course, as a secret nerd that you can aspire to have your research shown in this comic strip. But what you see here is you see this ring of light, and most of this is coming from the hot plasma around the black hole, which glows very brightly in radio waves. So this is all like a false color radio image. And the radio waves are bent around the black hole in the space-time of the black hole along this photon ring, which the innermost part of that would be the photon orbit, where photons move around the black hole possibly an infinite number of times. And then as you go farther out from that, you have fewer and fewer orbits around the black hole until towards the edge, you wind up seeing black photons that are just moving around the black hole or skirting the edge of that photon orbit. But this is something you only see for black holes. This is a smoking gun, if you will, for this being a black hole. And what's interesting about this is you see a brightness towards the south. And that means that you're seeing gas moving relativistically towards you. So it's moving so fast that it's what we call Doppler brightened or Doppler boosted. And the gas in the top is moving away from you, so it seems a little dimmer. And so that's one very important conclusion that we had never seen before. We've learned about that through simulations, but we had never really seen that in action before. Now we know that some of our best simulations are beginning to show us actually what's happening near the black hole. And then the size of it is very important because we can measure the mass of this black hole. Imagine being able to lay a ruler across space-time. That's what we were able to do with the Event Horizon Telescope. And by measuring that ring, and by going back to the fundamental equations of gravity, we were able to extract the mass of this black hole in a completely different way that we hadn't been able to before. And that's what gave us the 6.5 billion solar mass value for this black hole. So that's what you're seeing in this particular image. And of course, with the XKCD additions here, you see where Voyager is. That's the farthest person-made object that's been launched from our solar system. And then you see the orbit of Pluto. And it gives you pause. It gives you pause to know that you are inside that dark region which marks the event horizon. The reason you don't see light from that inner part is because the light rays and the radio waves that would normally come to us have crossed the point of no return and have been sucked into the black hole. Could I add one more thing, Peter, if you don't mind?
Yeah.
It is very important at this point. I want to show the whole collaboration. This is the engine that makes the whole thing run. This is about half of us. Only about 125 of us met in Hilo, Hawaii. And it was just a fantastic time to exchange ideas, to plot next steps, to go over the planning. You can see half of us here, and then many people also joined via Telecon link. So we're about 250 members strong across the whole globe.
That's a lovely picture. Thank you for sharing that and for giving this introduction. So, so do we have any questions from any of the participants?
And this is Rob from NSF. Just a reminder, if you do have any questions and you're a participant, go to the Zoom webinar chat window, select the all panelist option, and just enter your name in there. We'll get you queued up. If you'd like, you can also enter a question through Zoom's Q&A at the bottom, or you can just tell us that you want to ask a question through that, and we'll get you up right now. We're not seeing questions yet, and I'm sure we must have some. So, oh, okay, we got Mike Wall raising his hand. Oh, we also have a hand raising feature too, so we'll get better about watching that. Mike, I am going to turn on your, oh, we got Christian and Miriam too. So all right, we'll just go with the hand raising because that seems to be the easiest. And I'm going to get Mike in there first. And I apologize, like I said, this is our first time doing this, so we're still working out some of our own technical kinks. Mike, you are on, and I'm going to unmute you. Just make sure you're unmuted and your video is showing if you'd like, and go ahead and ask your question. Sorry for the delay.
Sure, thank you guys. This is great. Thank you for actually doing this. Just a quick question about the sort of next gen aspect of the telescope collaboration. Shep, maybe could you just go into a little more detail about what the current thinking is about what the next step will involve and what the envisioned timeline is? I know it's all dependent on funding and you can't really predict what's going to happen, but what do you hope happens and what do you think is going to happen with the next gen aspect and maybe getting something up into space? What's your current thinking about that possibility? Thank you.
Wow, these are great questions. Of course, this is what we've been preoccupied with for so long. So let me start off by saying that the EHT was really good value for the money. We went to existing sites around the world, and then we installed specialized instrumentation that allowed them to get linked up together to make a virtual telescope the size of the Earth. So we levered, I would say, billions, maybe $1 billion worth of international telescope infrastructure. And with a relatively modest investment, we made a completely new instrument. And we were just able to image this black hole. Now we can think about doing something different. Now we can think about putting telescopes exactly where we want them. So imagine being able to plot your own global telescope from first principles. And we can do this because some of the sites that we have, the ALMA array in Chile, the large millimeter telescope in Mexico, are so large, even a small dish can give you really good scientific data. So now we can put these smaller dishes in multiple locations. And what we want to do is double the number of dishes. And that would quadruple the number of interconnects between all the different dishes, which is the fundamental measure of how well you can make an image. So we're going to sharpen our image by doubling the number of sites. And when you get that many sites, you can also make snapshots with a very short cadence. So like every 10 minutes, you could take another image. And when you stitch those together, that's how we plan on making movies of these sources, especially Sagittarius A star in the center of the Milky Way. Now we have funds from the National Science Foundation to start this off. We would like to submit our designs in about 4 years, 3 or 4 years, with a full design, have the NGEHT up and running before the end of this decade. And then space, that's something that we're working on in parallel that may be a little bit longer. Maybe Michael would like to say a few words about that.
Sure. I want to add to what Shep was saying about what we can do from the ground first. When you look at the EHT image, we see this blurry donut, but that's not the only thing on the sky. And one thing that's limiting us is that we still have very few telescopes in the array. When we double them, it's not just that we get a sharper image, but it's that we see fainter things in the image, right? The rest of it comes into view. So to put this in context, every image ever made of M87 in history in VLBI has shown a jet. And it's very peculiar then that you go to the EHT and all of a sudden we see a donut. Where's the jet? It's not that it's not there, it's just that it's very faint. So for traditional VLBI arrays at longer wavelengths, they'll have a dynamic range of 1,000 or 10,000. And we have a dynamic range right now of about 10. So this is the kind of thing where we're really excited to pick these new sites around the world and to bring that jet into focus and let us understand how the black hole is driving it. And I think this is going to be one of the most rich sources of astrophysical discovery. For space, we've been really excited by the possibilities of thinking about extremely long baselines. And ordinarily, this would be useless for interferometry. Having just one baseline doesn't tell you anything. You can't make an image. That's why we need sites all over the globe. But it turns out that black holes are giving us this gift, that they have this photon ring that's very sharp and that will dominate the signal that you see when you go to these long space baselines. So what we're exploring is taking this dense ground network that gives us this whole picture and all these details and all the astrophysics. We drop down one long space baseline on top of it to give us this extremely sharp photon ring and to isolate all that general relativity. So we're right now looking at a lot of different mission concepts and trying to get a sense of what would be possible, both with missions that are already planned to extend them to include some some capabilities to join the EHT and for new dedicated missions.
Great, thank you.
Okay, so for our next question, we'll go to Christian Reddy. Christian, are you there?
Yes, hello, can you hear me?
Yes, we can.
Oh, thank you. I just wanted to ask, there was well, first of all, I'm from Launchpad Astronomy, and there were some images and even, I don't want to say movies, but some images made of a jet emerging from a quasar that was attributed to EHT. And I was wondering if you could speak a little bit to that. How did you find the time to tease that out of the data?
I'll say a few words about that, and Michael can also speak to that. So the Event Horizon Telescope has this extraordinary angular resolution, and it's useful for many things. The qualitative leap we made with the black holes was to make a first image of that photon ring that Michael was talking about, and that was truly like a discovery level. But at the same time, we can look at other sources where we can't resolve the event horizon. So this quasar 3C279 is one of those sources that is well known. It's very bright. A supermassive black hole at its center powers this incredible luminosity, this brightness. And there's also a jet that issues from the center of that galaxy almost directly towards us. So it's only offset by maybe 2 degrees from our line of sight. And we had never gotten as close a look at that source as we were able to get with the Event Horizon Telescope. And when the collaboration looked at that, we were able to see some kinks, some changes in direction, and some very interesting features very close to the black hole, within just a few thousand Schwarzschild radii of the black hole. So it was the closest look we'd ever gotten. We saw some very interesting new things there. And just as with the EHT results on the Event Horizon, there's more to do. We're going to be looking at magnetic fields that will help us disentangle some of the models that have been proposed for this odd behavior close to the core of 3C279. But it's a way in which the EHT can uncover a wide range of mysteries, not just at the event horizon.
Kristen, did you have a follow-up question, or are you satisfied?
Yeah, well, I did. It was a little bit of a second question, but to be honest with you, I completely forgot. I'll ask it when I remember.
Well, maybe I can answer one thing that you asked. How did we find the time? I mean,
Yes,
we're so busy here at the Event Horizon Telescope. How does one find the time? Well, so it turns out that 3C279 is an extremely valuable calibrator for us. So we observe it interleaved with the observations of M87 because it's so bright, it allows us to calibrate our instrument. But once we've calibrated the instrument, we can also use those observations to make images of that source. So it was first and foremost a calibrator, but also very scientifically interesting in its own right. It was part of the analysis that we had done even for M87. So it was done really in parallel with one of our primary targets.
Thank you. I did remember my follow-up, if I may ask.
Please go ahead.
Okay. Well, I wanted to know, I know you guys were working on Sagittarius A star, and I'm also well aware that this current situation has put a hold on actively collecting data. I was wondering if you could just discuss, in broad strokes, where you are with Sag A star.
I can say a few words about that. One thing that was really extraordinary for us in the M87 results is that we observed it for a week, swallowing as much data as we could. And the incredible thing that really caught us off guard is that it was changing before our eyes. And you don't even need to make images to see this. You can see it directly in the data, that the source on one day, it looks different than the source on observations a few days later. So this is a consequence of going to the extremely high angular resolution, that you're seeing things so finely on the sky that you can see things change over time. So for M87, this was kind of a slight effect. We get, it's like the little bit of motion if you take a snapshot on your phone. But 1 day in the life of M87 is a minute in the life of Sagittarius star. And so for Sagittarius star, instead of having something that's just gradually evolving over the course of a week of observations, we have something that can be violently evolving over the course of an hour. So this technique that we use, we try to gather data over an entire night and turn it into a picture. It's called Earth rotation synthesis, because we're using the rotation of the Earth to actually make better images. And that just simply doesn't work for our galactic center for Sagittarius star. So it's just a much more challenging problem, and to develop the same degree of confidence in our results is a much longer process.
Thank you very much.
Okay, then we'll go next to Miriam Kramer from Axios. Miriam, are you there?
Hi, I'm here. Can you hear me?
Yes, we can hear you.
Great. Hi, Miriam Kramer with Axios. I know you guys have touched on this a little bit, but I would love to hear, like, what effect is the pandemic having on your collaboration and signing new people on to this project, new observatories? Like, what are you seeing basically?
Yeah, let me. It's a very good question. We're all being impacted by this. This is a very, very serious situation. First and foremost, the safety of everyone in the collaboration is what we're focused on, and that was the primary reason why we had to cancel the observations that were coming up. We just could not ensure everyone's safety as they went to these different observatories and kept up their work. And then more than that, we're humans. We have families. We have big social connections, and it was just very, very difficult for anyone to really think about mounting an observation like this in these times. But even so, we're able to do a lot of the work that we're committed to. So, for example, we spend a lot of our lives on Zoom anyway. It's horrible to think about, but we're on Zoom almost constantly anyway because of the very nature of this collaboration, and it's the far-flung membership. So it's not uncommon for us to collaborate, to even analyze data, to show plots on screens in real time, while we have maybe 20 or 30 people on the line from all over the world. So in that sense, we're able to continue a lot of the analysis that we're working on. What has stopped a little bit is of course the observations, and it was heartbreaking really for a lot of us to have to cancel because we had put so much time into it. People from all over, all the telescopes, the operators had put a lot of effort into readying these observations, which would have added 3 new sites really to our array: a site in Greenland, the Noema site in the French Alps, and then the Kitt Peak site in Arizona. So we would have gone from 8 telescopes to 11, and that would have really helped sharpen our images and help with the time analysis that Michael was talking about. So we're adding new members all the time, no matter these difficult circumstances, and we are itching to get back to work.
Great. And if I could just ask one quick follow-up. I'm wondering, do you have a sense of how long this might delay you guys? Is it still very much in flux as far as like, when things might be able to pick up again? I mean, obviously they are, because we're all dealing with the pandemic, but I'm curious if you have a sense of timeline.
Yeah, well, I'd be guessing here, but we're now looking forward to the 2021 observations. So typically we operate on a cadence of once per year. So hopefully, and I do emphasize hopefully, this will pass in its major impact on our operations before then. So we'd be able to stage some preliminary observations maybe in the late fall or November, December timeframe to get us ready for March and April observing in 2021. At this point, that's what we're thinking about.
Great. Thank you guys so much.
Shep, I wonder if you could just say a bit about, why observations once per year? What goes into when it is possible to make an observation?
Yeah, well, it's just a matter of geography, really. We have sites in the northern hemisphere and southern hemisphere, and the good observing weather, which we need, just happens to have a sweet spot around March and April for our 2 primary sources. They happen to be, nighttime sources up in the sky at around March and April. And the real measure of when the weather is good is there water vapor in the atmosphere. So you want it to be cold above you so the water vapor freezes out. So that argues for closer to the winter. But of course, in the northern hemisphere and southern hemisphere, the seasons are anti-phase. So you've got this one little section of the calendar when everything kind of conspires to come together. It's the Goldilocks spot where you can make observations around the world. So we tend to focus there. We have been talking about splitting the observations, maybe one focus on M87, one on Sagittarius A star, and also making observations throughout the year for parts of the EHT to start to see how these sources might evolve, as Michael was saying.
Any astronomer can appreciate the challenges imposed by weather. Most astronomers only have to deal with that at one location. You have a number of locations that you have to get right all at the same day at the same time. It's quite extraordinary. So our next question is from Dan Cleary from Science. Dan, are you there? Hi, Dan, are you there?
Can you hear me?
Ah, there we go. Yes.
Okay, hi, Shep and Michael. Thanks for doing this for us. I had a quick question. You, Shep, talked about this being the start of precision science with event horizons. Can you talk about some of the science that might be possible when in the future you've got the next generation array and possibly an antenna in space? What sort of science will be possible?
Sure. Let me. I'm going to share my screen quickly because I want to make a point that Michael discussed before. Can everyone see this? Peter, is this coming through?
Yeah, I can see it just fine.
So this makes a point that Michael was stressing before. On the left, you see a simulation. This is some of the best physics we have, simulating what the black hole actually looks like. And in the inset, you see the black hole image that we've been looking at so far. But you also see this jet structure going out to the right. And this is one of the fundamental properties of black holes. And this is why we really care about them. They show this event horizon, but they also power these jets that can pierce entire galaxies. And really, they affect the night sky that we see. Now, in the middle panel, you see what we, the image in the inset is what we actually can kind of image now, as you've seen. But it's very difficult for us to take a high fidelity image of that jet because we don't have enough sites around the globe to tell us where all that brightness should be. And our algorithms for imaging get very confused. And they don't know how to make the image of the jet. We just don't have enough information. On the right, you'll see the NG-EHT and what we can do there in this simulation. And you can see that we can make a very high fidelity map of how this jet is launched. And so this fundamental mystery of how jets are launched, how these black holes send out these jets of relativistic particles, that's something that the next generation EHT is going to focus on. It's like a fundamental new topic. So that's right.
We're back.
There we go. Yeah, there we go. Am I still sharing my screen? No. Okay.
Not anymore.
So that's one of the answers, Dan. And then I'd like to, maybe Michael would like to chime in on test of GR with space.
Sure. Maybe I'll show a video.
Oh, this is really cool. Are you going to show the one that you're thinking of, that I'm thinking of?
I think so. So the idea is very simple, actually. You know, we talked about this shadow of a black hole, and that shadow carries the imprint of the black hole. So it takes this unique signature of how the black hole is distorting its space-time, and it puts it on the image for us. And it turns out that leads to a number of rather extraordinary effects. So I'll just play this movie. Do you see it playing?
Yeah, it's look. Yeah, now it's going.
So what's shown here is just light rays that come near the black hole. And they're coming fairly close. And so the black hole actually bends them around, and that produces this image. So we label it n equals 0 because the light just sort of got weakly bent by the black hole. If it comes closer, it can actually loop around the black hole before reaching the observer. And it turns out that then the light collects on this, this very special region, this photon ring, and it produces a sharper image. But black holes are amazing. They can actually loop light around as many times as they like. It just has to be shot closer and closer to this critical curve on the image. And so here is just showing the image contribution from light rays that looped around a full time before reaching the observer. And so when you take all of those light rays together, then you get the complete image that a distant observer would see, something like this. So this is a simulated image. This is produced by George Wong at the University of Illinois and the group there, who's done a lot of the pioneering theory work for the Event Horizon Telescope. And you see that this image really contains a stack of rings, and each ring has about the same diameter, but they get sharper and sharper. And as they get sharper and sharper, they're honing in on a pure signal from general relativity. It's almost a perfect circle. So the diameter of that circle, that's the thing that tells us how big the black hole is, the mass of the black hole. But it turns out that if the black hole is rotating, it squishes a little bit on one side. So this particular one isn't a perfect circle. It's distorted by just a couple percent where it becomes a little bit elliptical. And that's the imprint of the spin of the black hole. And that's something that we could measure if we went to long spacelines. But the beauty here is that we think that black holes are completely described by these two parameters. And so by reducing it down to this simple problem, measuring the size and shape of this ring on the sky, we're able to test general relativity in a new way, where we think we know exactly what it should look like. There's no levers, there's no uncertainty, there's no messy astrophysics. It's a pure signal that was written down decades ago by black hole theorists. And so by creating these sharper and sharper images, we're able to put that to the test and to see, do we really understand how light is bent by a black hole, even when it's being looped around many times and approaching closer and closer, to these very special regions defined by the black hole's space-time.
That's fantastic. Thank you. Dan, did you have a follow-up question?
No, that's great. Thanks very much, guys.
Okay, thank you. So next on our list is Georgina Torbett from Digital Trends. Georgina, did you want to ask your question, or shall I just ask it for you?
Oh, yeah, I was just wondering if you could tell me a little bit more about the plans to create a video of the black hole, and if the technologies you'd use for that would be different from the ones you used for the photograph. Thanks.
Okay, I can start that one. And by the way, I want to say that image, the simulation that Michael just showed, it just knocks my socks off. I mean, that's, being able to have access now to multiple photon orbits is just something we couldn't even have imagined before the Event Horizon Telescope. So it's an example of how it's changing our way of thinking, just our approach to the science of black holes. And it's being it's fruitful because we're getting all these new questions coming up. So about movies, there's a couple of ways we can approach this. For M87, which is a monster, it's 6.5 billion times the mass of our sun. The time it takes an object to orbit around the black hole at the innermost orbit, the closest orbit that matter can move around, is on the order of days, more likely a month or so. So if you wanted to see the black hole evolve before your eyes, you would do it with time-lapse photography, right? You would take an image 1 week, and then a week later, and then a week later. And if you did that over a few months, you would have a movie you could play back that would show you how the black hole is changing its shape, how the plasma around the black hole is being shocked and dragged around, how jets are being launched from the North and South Pole. And that would answer a great number of questions for that source. And then, as Michael said, Sagittarius Star is a completely different animal. It's 4 million solar masses. So it evolves so quickly that objects would orbit it in half an hour. And so trying to capture an image of that is, unfortunately, like opening up your lens cap and exposing your film while a runner sprints by. It's going to be very blurry. But if we can take snapshots, then we'll be able to stitch those together to make a movie. And for that, people like Michael and others are developing new algorithms that go beyond this Earth rotation aperture synthesis that he talked about. Instead of combining all the data from one night, they look at snapshots and then make sure that they are fluid and continuous as we reconstruct a movie. But Michael may want to say more about that.
Yeah, I'll just say we are doing a lot of work on the algorithm side, and here it's been really fruitful to interface with other communities. The computer science and computer vision communities have a lot of techniques that haven't been brought to the world of radio astronomy yet. And so I think that there's a lot of promise for pushing those and doing better with the data we have. But fundamentally, we are data starved. At some point we squeeze as much as we can out of the data, and we want to retain the capacities to be surprised. We don't want to over-engineer the problem so that we're just getting back out what we expected to see in the first place. And this is why it's so critical to add new sites to the EHT. As Shep said, if we double the number of telescopes, we increase the number of data points that we get by a factor of 4. And that's just a world of difference. We're still in the regime where every new site we add, it completely changes the possibilities for what we can learn from this instrument. So it's what's exciting now is that we're in this development phase where we're trying to merge these two things. We're trying to design algorithms and then give input to where the new sites are going to be located, how big they're going to be, how to design this instrument so that we can get the most science out of it that we possibly can. And I think that carrying this EHT approach, where it's been a really continuous exchange of information all the way from people operating telescopes to people generating these numerical simulations, and putting that into the spirit of designing the next array is a really important aspect of how we're doing this.
Was there any follow-up question, Georgina?
No, that's everything. Thanks very much for the answer.
Absolutely. So I think our next question is from Marina Corin from The Atlantic.
Hi, everyone. Can everyone hear me okay?
Yeah, I can hear you, Marina.
Great. So this is I asked this question in the chat, and Shep, you addressed it, but I don't think you answered it, so I just want to ask it again. Obviously, the EHT is a truly global effort that relies on a kind of collaboration and connection that, because of the pandemic, doesn't really exist anymore. And it's hard to predict what form it might exist in the future. I mean, after this is all over, we might not have the same sense of global connectedness that we had last year. So I'm wondering if you think EHT will ever be able to replicate the kind of international infrastructure that you need to, that you had when you made the first black hole picture.
Mm-hmm. Yeah, I'm sorry if I didn't answer it completely in the chat. I would turn this around a little bit, Marina, and I would say it's exactly collaborations like the Event Horizon Telescope that are going to help pull us out of this sense of despondency that we find ourselves in. I mean, we're in a low point now. We are sequestered. We're in our homes. We're interacting remotely. But this sense of connectedness that we've had with the Event Horizon Telescope is going to carry our project through. And I think we're going to emerge from this with even a renewed sense of purpose and a renewed sense of connection and collaboration. We are spending all of our time on Zoom chats right now and analyzing data and plotting for the next steps, but we're doing this with such great energy. So I would turn it around and say that I think the EHT started something that you can't quench with one even global episode like this. And I think that we can look to collaborations like this as the way forward. I like to think that it's a silver lining in what's happening right now in our world and in our universe, that we can continue some of this aspirational work, that we can still communicate to the curious public and to journalists, so we can still keep the black hole fires burning in this time. So I think of it as very positive, and I think that we'll have no problem reconstituting things for our observations.
Could I ask a quick follow-up to that just now?
Sure.
Yeah, sure.
Yeah, I mean, I appreciate that sentiment. I also hope that we come out of this pandemic a little kinder than when we went in. But I'm wondering what your approach will be to, you know, just rules and regulations and, you know, lawmakers who don't necessarily have the same view that scientists do, that this is the kind of thing that can't be quenched. Like, how are you going to approach roadblocks that are not scientific and more, I guess, political and out of your control that way?
Well, the answer is I don't know, Marina. I truly don't know. What I would say, though, is that the EHT has been in the business of nimbly sidestepping a lot of political issues, a lot of logistical issues. If I had a nickel for every time I'd been told this can't be done, I'd have quite a few nickels. And I think it's the resilience of the collaboration and the goodwill of everyone that has allowed us workarounds. I mean, in an age where so many things divide us, Marina, the EHT found a way to work across borders. We found a way to share resources. We found a way to get everybody what they needed in order to satisfy their own constituencies. And I'm just confident that we'll be able to continue to do that. It's interesting, Peter said at the very beginning that we had brought people together in Washington, D.C. It was kind of a rare thing. And one of my great memories of this was testifying before Congress with Dr. Franz Cordova, the head of the National Science Foundation at the time. And it was just wonderful to be able to discuss this at Congress and talk to Democrats and Republicans and everybody. And everyone saw the utility of it. Everyone saw the promise. Everyone saw the impact. And I think the more we do that, the more we'll be able to address these challenges. I don't know exactly how we'll do it, but I'm very, very confident.
All right, thank you, Shep. I appreciate your time.
I just want to add that, you know, across the collaboration now, there isn't a tone of despair. I do think we're sort of united by the suffering, and you know, we have a lot of, I see Shep laughing. Yeah, we're a collaboration defined by suffering, even before this. But more seriously, I mean, the young people in the collaboration aren't, you know, moping and wondering what are we going to do without this year of data. They're busy scheduling virtual workshops and figuring out how to keep the work moving forward. You know, adjusting time zones, understanding the difficulties that each person is going through. So I really do see this as really a point of unity. And even these recent press releases, right? We just put out these new EHT results that were led by Jae-Young Kim at Max Planck Institute for Radio Astronomy in Bonn. You know, these came in the middle of a global health pandemic, and people were still enthusiastic about them. I think, you know, raising our eyes to the sky and remembering about, you know, these profound truths that exist beyond the details of the human condition. You know, this will always have a place. The black hole solution was derived by Karl Schwarzschild in the trenches during World War I. You know, so science continues, and I think it has an important role even amid these challenges.
Okay, so our next question is from Lisa Grossman at Science News. Lisa?
Oh, hi, I'm here. Thank you for doing this. I think that my question has actually already been asked. I was going to ask about making videos or movies of the black holes with the existing data. And I think that's actually been covered pretty well. So just thank you very much for doing this.
My pleasure.
Okay, thanks, Lisa.
So next we have a question from NSF's own Alison Farrell. Alison, are you there? Alison? Okay, well, maybe while she's getting set, we can go to Greg Redfern at WTOP. I see I have the question printed for me, so I'll ask it, unless you're there, Greg. The question is, what is the status of the EHT observations made previously of Sagittarius A star? Are they still being reduced? And if so, when might we expect to see the results?
Okay, I'll start to address this. This is a question that we get a lot. It's a great question. It's a natural question. And Michael touched on this a little bit. One of the challenges for Sagittarius A star is that it does evolve so quickly during the course of an evening. So we're developing new algorithms that can specifically address that to add a time variability to the modeling. That just takes more time. And I would point out that from the time that we observed M87 in 2017 until the time we came with our first black hole image was 2 years. And the reason it took 2 years is because we were being very, very careful. I want to make the point here that one of the things that I think should be made clear from the EHT experience is the scientific process, that we are really working very, very hard to make sure that we get the answer right. And we go down a lot of rabbit holes, we make a lot of mistakes, and it's only through this process of failing and then reanalyzing the data and then convincing 200 people across the collaboration that we've got it right, that we are confident in our results. And then we publish them in peer review journals that independently look at everything that we've done, and only after that do we release the results and the data. So it's a very careful process, and so it is taking us time to analyze the Sag A star data. When it comes out, we will be giving everyone the best view that we have of it, and we'll be confident that we have gotten what we say right.
Okay, thank you. And I think now we're ready for Alison. So this is Alison Farrell from NSF. Are you there, Alison? Okay, maybe still having, Alison, you might be muted perhaps. Okay, maybe we've lost her. That's okay. So just as a reminder, if you have any other questions, you can indicate that by raising your hand. Shep, you know, one of the things I was hoping to ask you is just looking back over the past 12 months, culminating, you know, years of hard work. How does it feel? And I wonder, do you have any kind of advice that you could give, or any lessons learned or thoughts for other people who are working in science or in other areas of their life to bring something challenging to fruition? What has this meant for you personally?
Well, it's a very good question. Well, first of all, the experience of imaging this black hole after, you know, so long and with such a great team was incredibly uplifting. I mean, everyone should have this experience, right? Everyone should have this amazing goal that they're working on. Have you know, colleagues from around the world to join you, and to then see it come to life. Has been really the experience of a career. It'll be hard to top. Let me just say that. But it's also, you know, there's some obligation that comes with it too, because we have to take the next steps now. I mean, we always build on what came before, and this, from a personal standpoint, this really connects us as a collaboration and personally to people that came before. So there's, you know, Einstein, Schwarzschild, you know, Kerr, all the people that started thinking about the theory of black holes, and many others, and even Stephen Hawking, who sadly did not live to see this, although he knew about it, and how wonderful it would have been to describe to Stephen and even to Einstein in imaginary conversations what we've done. I mean, I just can't help but think they would be overjoyed, but also blown away. And so it is something, science does connect us with others over the bridge of even 100 years. And that's something that I think is really remarkable. I'm sure Michael has his own, Michael's been in the thick of it, so he probably has his own feelings about it too.
Any thoughts, Michael?
Yeah, I think, the process of doing research is very different than the process of learning about research. And I think my advice to people who are aspiring to be science researchers is probably don't walk around waiting for some, flash of insight, some moment where you come up with a new theory that you then write down and, supersede Einstein or something like that, which is, I think, in many ways what we're raised to expect, that these come through these moments of discovery. And instead, it's this multi-year slog through incredibly challenging problems that you can only do by surrounding yourself with just incredibly talented colleagues who bring all sorts of skills that we can't all hope to have. So I would just say, groundbreaking research is possible, but roll your sleeves up and be prepared to just slowly bend nature to your will. It's a difficult process, and but it's so exciting that these fundamental discoveries are still there to be found. So yeah, I mean, I find it just really, really inspiring to be part of something so ambitious.
It seems to me that one of the recurring themes that's emerged from your comments and Shep's, as well as some of the earlier discussion, is interconnectedness and interrelationship, and how important that has been to the EHT's success, being interconnected with collaborators on different continents and different institutions. And also, as Shep is pointing out, this connection that you feel now towards scientists of previous generations who have paved the way for this work in progress now. I wonder if one of the overarching themes might be the importance of surrounding yourself with good friends and creating that environment where people can work together.
Yeah, I think it's very important. There's one element that I would stress too, is that you really have to learn to eat failure for breakfast. I mean, you just have to be comfortable with failure. You have to sit next to it, have a drink with it, and know that it's just going to be with you forever, and that it is really good to have it with you, because failing gives you the ideas of how to improve things. It makes you resilient. What I tell people is that in 2006, we mounted observations to measure the size of the black hole in our Milky Way galaxy, Sagittarius A star. And after many months and even a year of preparation, we went and we failed. There had been a malfunction in one of the pieces of equipment. And we spent months fruitlessly searching through the data to try to find this detection that would have let us size this black hole. And when we realized that we had failed, then we knew what we had to do the next time. We rolled up our sleeves. We added another antenna. We made the group larger, and then we went back again. And that was in 2007, we made observations where we were able to detect Sagittarius A star and tell what the size was. And so you have to be able to pick yourself up off the ground and dust yourself off. And it's made easier, to your point, Peter, when you're with a bunch of wonderful colleagues, because that's what allows you to work together to overcome not only the technical challenges, but some of the personal feelings that accompany failure.
Right. That seems to me one of the hidden stories that sometimes doesn't make it into the headlines about science, is that behind the scenes, there's quite a bit of trial and, as you say, failure.
Oh, the sausage making is a whole nother story that needs to be told.
We have a question from Rick Feinberg from AAS and Sky and Telescope. Rick, are you there?
Yes, I am. Thank you. So I was surprised earlier this week when that paper came out about the image of the jet in 3C279, because I figured the next time we heard from you guys, it would be Sag A star. I'm curious if you can tell us about any of the other interesting types of objects that you might have also looked at and that we might see some images from in the coming months.
Well, I'll maybe mention a few. You know, as Shep said, a lot of these sources, we observe them, you know, we fondly call them calibrators. We interleave them with observations of Sagittarius star and M87, but these are rock star sources in their own right. So one source we observe a lot is 3C273, which was the first quasar. Another source that is really exciting is OJ287. So this is actually one of the best candidates to be hosting a binary supermassive black hole. So this is not, you know, just one black hole at the center of the galaxy, but two that are orbiting each other on a time scale of 12 years. And it turns out that their closest approach is about the same as the resolution of the EHT. So if this is really two black holes that are spiraling around each other, there's a chance that we could be watching that in action and tracking that over years, seeing these black holes orbit each other. So those are, you know, just two of the other sources we look at. But really each of these, you know, we're looking at blazars, and, you know, we're looking at these quasars, dual AGN, and so forth. And in the future, we're hoping with the expansions of this next generation Event Horizon Telescope to look at other types of objects too, like astrophysical masers. So it's really exciting to kind of expand our view from the event horizon and out to these larger scale systems. Shep, did you want to add any more on that?
Well, it's there's like a treasure trove. You know, we have these nice observations from 2017, as Michael said, with a lot of sources, and now we're looking at the 2018 observations, which is really interesting, Rick, because for M87, for example, once we start analyzing 2018, then we'll have a look at the ring around M87 after a year, and so you'll be able to see the long-term behavior of M87. And the other thing I would add to Michael's good answer is that having these extra sources gives people visibility within the collaboration. So Michael pointed out that Jae-Young Kim was the researcher at Max Planck Institute who led the 3C279 observations, with a lot of help, of course, from all over. But these other sources, they're not event horizon sources, are one way that groups within the collaboration can focus on things and you know, really target them in a certain way and get some credit for it. So it's really lovely to see that.
Rick, did you have any follow-up?
Just a very quick one. So we've heard about M87 and Sagittarius star, especially with the next generation EHT. Do you anticipate being able to reach toward the photon orbit for any other of the supermassive black holes around us, or is everything else just too far away or not massive enough to be big enough to resolve?
Michael, do you want to take this first?
Well, you know, LIGO is an interesting story, right? LIGO observed for decades and had nothing except fake detections and so forth. And then all of a sudden they made their first detection, and a few years later, you know, they're detecting something every month, and it just changed very fast. And for the Event Horizon Telescope, we have sort of a similar situation where the scaling is volumetric. So if we double our angular resolution, the number of black holes where we can study them on horizon scales goes up by a factor of something like 8. And if we can put a telescope, add telescopes to the EHT to the moon or to L2, there might be tens of thousands or even millions of sources where we can study them all of a sudden with horizon scale resolution. That said, as we go to these long baselines, Sagittarius star and M87 are always going to be our special sources, right? They're the biggest black holes on the sky anywhere in the universe as seen from Earth, and they're going to be the ones where we look deepest and we study general relativity the most carefully. But absolutely, as we push to higher resolution, either on the Earth by going to higher frequencies or by adding new sites in space, you know, we're going to see a zoo of black holes, and there's really a lot of exciting possibilities there that we're just beginning to explore.
Can that was great, wonderful answer, Michael. I just love the LIGO connection. I think it's really true. This is just the beginning. We'll be looking back on this 20 years from now. We'll all be drinking, umbrella drinks somewhere, and I think we'll recognize the M87 image as just the beginning. It really will be just the beginning. And this is what they say about Galileo, right? I mean, when Galileo first looked through the telescope, the first telescope, it wasn't the end of astronomy. It was just the tip of the iceberg, just the beginning. And so I think that this discovery is going to keep rolling on. The other thing to note is that it's not just the baseline length. So you can also increase the angular resolution of an interferometer by looking at higher frequencies. So it could be that as we move from this frontier frequency, or we think of it as a frontier frequency now of 230 gigahertz at which the EHT operates, if we move to 345, that would increase our angular resolution immediately by 50%. And then if we could find the best places on the Earth to do even higher frequency VLBI, we could increase it maybe even by a factor of 4. And then going into space, of course, is the next step. So you wind up with in a situation where there are multiple ways of getting higher angular resolution. And as Michael says, with angular resolution comes more sources that you can look at. So there may be just a few that we could do from the surface of the Earth. And then as we go into space, more targets will come into range.
Thank you.
Oh, one last cool thing is of course that, and this gets back to Michael's photon ring point, that the photon ring is set by the gravity, and light of any wavelength is lensed in the same way around that black hole. So if you can start to merge the data from different wavelengths together to give you a better look at the photon ring, because the size of the photon ring should be the same no matter what frequency you observe it in. So you can start to combine multi-wavelength data sets in a way that you can't with typical astronomical sources.
Okay, we have another question. This one from Randall Hyman from Astronomy Magazine. Randall, are you there? Okay, I think the question, it's been typed into the chat. So the question is, will the upcoming 2021 observations all be at 0.87 millimeter wavelength?
Yeah, so that's a great question. So for the observations that we had canceled in 2020, we had reserved an entire night only to look at that new frequency. So we had already lined up a smaller array, because not every telescope in our array can observe at that higher frequency. And sadly, of course, we had to cancel the observations. So we are aiming over the next year to keep up the tests at that new frequency, get ready for 2021. And then in 2021, we would hope to at least repeat that cadence where we had 7 days of observing, and one of those days was earmarked for the higher frequency. But if everything goes well, we might even expand that to be more than 1 day. We don't know at this point, but for sure, we'll be looking to have some observations in 2021 that will increase the frequency and the angular resolution.
Okay, thank you. So it seems like we've come to the end of our questions, unless anyone has anything that they'd like to raise their hand for right now. And before we conclude, I wanted to take some time to thank everyone who's participating today. Thank you, all of you from the media for dialing into this event. And of course, thank you, Shep and Michael, for taking time to be here with everybody today. And I also wanted to thank everybody at NSF. The Office of Legislative and Public Affairs has been working really hard on a fast timescale to make this event happen and have it all come across in an organized way. And it's really a pleasure to work with all of you. So thank you, everyone, and good luck. Stay healthy, stay safe. I think I'll turn it over to Rob Margetta for a few final concluding comments.
Actually, Peter, could I say one thing before we wrap completely?
Yeah, of course.
I just wanted to make sure that everyone knew that the sites around the world are, we're so fortunate to have the investment by the global astronomy community in all of these sites. And I just want to point out that we use sites in Europe, the IRAM facilities, the 30-meter dish there, the interferometer in the French Alps, Plateau de Bure. We have a new site in Greenland that is run mostly by Asia A and Taiwan. In Chile, we have ALMA and OPEX that are joining. In Mexico, at almost the geographical center of our array, we have the Large Millimeter Telescope. We have the SMT in Kitt Peak in Arizona, the Submillimeter Array and the JCMT on the island of Hawaii, and the South Pole Telescope at the bottom of the Earth, where the Sagittarius star is circumpolar. It never sets. And we're seeking new partners to extend the array even further. But I just want to extend our heartfelt thanks to all those facilities and to the people at them that really make the EHT happen, as well as another shout out to all of the members of the EHT that are working so hard to make it possible. So thanks.
Absolutely, and congratulations once again. Rob, over to you.
Just some quick housekeeping notes. Again, thanks to all the panelists. This has been really great, really useful. Thanks to AAS and the DC area science writers for letting their members know about this event. And just to everybody on the line, NSF is trying to reach reporters to serve them as well as we can in an obviously difficult situation. We know that a lot of people are stuck at home and don't get the usual access to experts and events that they normally can. So we're trying to fill that gap as best as we can. If you have any suggestions for sessions, if you have any format notes from this that you think we might find useful, if there are any subjects you'd like to see NSF or its experts cover in a forum like this, in sort of the same scenario, you get 60 to 90 minutes to just really ask whatever you'd like. Please let us know, because we're really trying to make an effort to serve the science writers community here. And again, thank you all for your time, and take care.